Welcome students. Today we will discuss De Morgan's laws, in which we have two De Morgan's laws which will be used to simplify the Boolean expressions. Before going to the main topic, let's have a recap on the previous topics. The last class we have discussed about the fundamental logic gates, and in which we have discussed three logic gates, which are inverter gate, AND gate, and OR gate. The corresponding truth table is given here. Inverter gate invert the input signal or input variables into its complement, and AND gate basically give the output in terms of the product. That is, if we have input A and B, then the output will be A dot B. And in OR gate, the input variables are summed. That is, if we have A and B as an input, then the output will be A plus B. So in this class, you will learn and explain the De Morgan's law. And also, you will apply the De Morgan's laws to solve the Boolean expressions. Let's start the De Morgan's laws. It can be stated as the complement of the product is the sum of the complement. That is, if we have two variables x and y, then the product is a x dot y and its complement is written as dash. So x dot y dash will be equal to the complement of the sum of the complement of the variables x and y, that is x dash plus y dash. The complement of the sum is product and of the complement, that is this is the second law, x plus y bar, that is dash, is equal to x dash dot y dash. So these are the two De Morgan's laws. One is the complement of the product is the sum of complement, and another is the complement of sum is the product of the complement. And we can generalize this law for n number of variables, and it can be proved by using the truth tables. So we will prove these two laws by using the truth table. So in the first case, if we see x dot y complement is equal to x dash plus y dash. So let's say we have two variables x and y, and in the first case, first combination of the inputs, that is x is 0 and y is 0, x dot y will be 0, and its complement, that is the complement of x dot y, will be 1. Similarly, the sum of the complement, that is x bar plus y bar, will be 1. And now for the second case, if you see x is equal to 0, y is equal to 1, then x dot y will be again 0, but its complement will be 1. Similarly, x bar plus y bar will be also 1. And in this way, we can verify that whatever be the value of x and y, the complement of x dot y and the sum of the complement, that is x bar plus y bar, both are equal. So this is the LHS and this is RHS, so both are equal. So we can write this in terms of a formula that is called De Morgan's law. X dot y whole bar is equal to x bar plus y bar. Here we have written dash. So we can prove the De Morgan's law for the second one also by making the truth table like this law. Morgan's theorem can be proved by using the logic gates also. You can see here x1 and x2 are two variables, and if it is working as an input for an AND gate, and the output will be x1 x2 bar, and this will be equivalent to logic gate in which x1 and x2 are first used as a variable for two NOT gate, and then it is complemented, and the complemented variables are now act as an input for OR gate, and the corresponding output is x1 bar plus x2 bar. So this is the first De Morgan's law. And in the second case, if we have two variables and it is if these x1 x2 are inputs for NOR gate, then x1 plus x2 whole bar will be the output, and the x1 bar x2 bar will be obtained by this gate, which initially the NOT gate are used, and then one AND gate is used. So these two outputs will be equal. So we can express the De Morgan's law by corresponding digital circuits. So here some practice questions are there based on the De Morgan's theorem, because after knowing the laws to De Morgan's law, it is very important to use those laws to simplify the Boolean expressions. So here the Boolean expression is given. It is A C D bar plus A bar B inside bracket C D plus B C bar. So we have to solve this Boolean expression by using the De Morgan's law. So first we apply the distributive law to the second term. So here this is the second term, and if we multiply A bar B with each term inside the bracket, we will get ACD bar plus A bar BCD plus A bar BBC. Since we know that B dot B is equal to B, so we further simplify it in step 2. So after simplification, it becomes x is equal to A C D bar plus A bar BCD plus A bar BC. Now C is common, so we take it outside the bracket, and AD bar plus A bar BD plus A bar B will be the expression. Now in the fourth step, we see that A bar B appears in the last two terms in the bracket. So we take outside, that is A bar B, we take outside, that is D plus 1, and since D plus 1 is always 1, so we write x is equal to C A D bar plus A bar B. So this is the simplified version of the given expression, and now from this expression we can design the digital circuit in which two NOT gate, two AND gate, and one OR gate is used. So earlier the logic gates was large number, now it is simplified, and we have reduced the number of logic gates. So we can say that we have reduced the processing time because we are using very less logic gates. In this problem, we will solve this Boolean expression and simplify it by using the De Morgan's law. So the expression is a plus b bar plus c plus b plus c bar a whole bar. So this is the expression. Now we will solve it by using De Morgan's theorem. So if you apply the De Morgan's theorem here, we take this bracket as one term and b plus c bar as one term. So using the De Morgan theorem, it will be a plus b bar plus c bar dot b plus c bar whole bar. So this is the De Morgan's theorem. And now further, in this bracket we can use the De Morgan's theorem again. So this becomes a bar plus b bar over bar. So it becomes b plus c bar, and this is again solved by using the Morgan theorem. So it becomes b bar dot c bar over bar. So it becomes c. But the interesting thing is the the term b and b bar are here, and as we know that b dot b bar is always 0, similarly c bar dot c is always 0, so this entire term becomes 0. So uh, the expression for this means the solution for this function is Boolean function will be 0. So whatever be the value of variable a, b, c, the output will be always 0. It means we don't need any logic gate because every time we will get output 0. So neither we can use NOR gate, NOR gate or AND gate. So whatever we the inputs, we will always get output as 0. This is because we will have this De Morgan's theorem, and we have used that to simplify this. So this is the application of De Morgan to the laws that we have studied. These are some references for the topic. You can go through this books for better understanding. Thank you.